Well, I hope everybody had a nice weekend. It was pretty miserable weather out there, and looks like it's maybe just getting even a little bit worse. So hopefully you were able to stay comfortable and warm over the weekend. Do something nice. Let's start with look at what's coming up on the schedule. And so homework 2 is due on Wednesday before class. And as you have questions on that assignment, I invite you to call me on Teams, call me on the phone, send me an email if you need, and I'll be glad to respond. The only thing that is maybe not a great way to get a hold of me is there's a chat tool within Teams, and for whatever reason I don't see those messages very easily. You know, like you can text chat through Teams, and especially on the weekend those notifications don't get through to me, and I don't view that as often as I would just a normal email. So if you want to get in touch with me to ask questions about the homework, I'd be glad to hear from you, and just please let me know how I can help. What we're going to do today is look at a video that I kind of skipped over in a previous lecture because we were running low on time. A video that shows how to solve the Colebrook equation with an HP calculator. And they don't really make as many HP calculators as they used to, but there are emulators available where you can run an app on your phone that simulates this calculator. I'm holding up a physical copy of it. It's out of production now simply because there just wasn't enough demand. People were too tempted with the cheaper calculators to spend the real money on a machine that's worth their time. You can tell I have an opinion about that. I will try to avoid getting on the soapbox too much today, but I want to show you what it can do. $500 on Amazon, yeah, but you can find it for like $130 on eBay. You know, anytime something is no longer produced, there will be people who are trying to charge a bundle. But the emulator is either free if you've got an Android phone, or $8 if you've got an Apple phone. So that's maybe good enough. We're also going to talk about a little bit more of the comparison of empirical resistance equations. So we'll do a head loss comparison for the same scenario, calculated 3 different ways. We'll look at what's the head loss if we do it Darcy-Weisbach versus Hazen-Williams versus Manning's equation, and we'll also go through an example that I sent you the template file before class. I emailed you a spreadsheet that has kind of the starting point that we're going to use for a pipe sizing problem. One thing about the breakout rooms, I did hear back from IT, and apparently it's a known issue, and what it's usually in the past been confined to was the last breakout room. So like if there are 6 of them, it's a known issue that group 6 will maybe have audio problems. Or if there are 12 breakout rooms, it would be room 12 is the one with audio. And they say the solution to that is just reassign people in that terminal room to a breakout room that does have functioning audio. So we'll see if we can figure that out today, and if really the issue is confined to the last one, or if it's maybe more widespread than they suggest. Now first, let's go through this example on how to solve the Colebrook equation on the HP calculator. And it's not just because I'm trying to make you feel bad for using the Casio. I think the HP is the superior tool, and I want you to have the tools you need through your college career and also your professional career to solve complex formulas as easily as possible. And so what you're going to see in this example, it's a previously recorded video on YouTube that just shows solving the Colebrook equation. You're going to see that the calculator allows you to construct equations in a graphical way that's really not possible with the Casio calculator. So we'll look at that demo in just a second, but I sent you the email earlier that says where you can find the emulators and a little bit of details on how to configure that. Alright, so let me pull this window over, and we are going to look at how you solve the Colebrook equation on the HP 50G. Okay, so I would just put it out there as a tool that's worth checking out. You know, learning how to use the emulator on your calculator maybe will take 20 or 30 minutes to get it set up and get accustomed to where the buttons are and learning how to use the equation writer, you know, it's not a zero investment. It will take some time, but then the dividends will just pile up year after year forever. And it's the sort of thing where you're going to be in the career, your job is doing calculations, so wouldn't you want the most powerful tool for doing calculations that you can get your hands on? Like, you know, if your job is to be a writer, you wouldn't just get a free pencil that came with a Happy Meal. You'd maybe, you know, invest in a good writing instrument that's comfortable in your hand and has a nice clear ink that comes out of it and everything. So, all right, that's solving the Colebrook equation with the HP calculator. Now, let's do this. Let's do this head loss method comparison, where what we're looking to do is compare in relative terms the Hazen-Williams equation, which is the top one, Manning's equation here in the middle, and then the Darcy-Weisbach equation. And you'll notice that I provided the Jane equation here, so that's a little bit easier than using Colebrook equation. But we're going to compare the head loss that we get from these three different methods to take a look at how far they differ from what we know is the most accurate. We know that the Darcy-Weisbach equation is the most accurate means of characterizing head loss through this pipe, where water is flowing at 1 meter per second, so that's within the limit that we talked about before for the Hazen-Williams equation. It should be under 3 meters per second, so we're in that range. Also, it's water, which is what the Hazen-Williams equation is calibrated for, so we're obeying that requirement. It's within the diameter range that's acceptable for Hazen-Williams, and so we're not way off in left field here. We are using Hazen-Williams within the zone that we should be. But let's see how different it is from Darcy-Weisbach. And then Manning equation, I told you that one's not really so good for closed conduit flow, and you're going to see why in just a moment. So I'm going to put you into breakout rooms to work this example and check answers with each other and talk about whatever you like. How was your weekend? But let's also text to see if the audio in your breakout room isn't working. Please put a note in the chat area just so that I'm aware of it and so that I can move the people who are having no audio into a different breakout room. I'm really kind of fixated on trying to troubleshoot this issue because I'm hopeful that it could be such a useful tool for us through the semester to have these smaller breakout rooms. So we're going to work this example. Let me set you in those rooms now. Welcome back, everybody. All right. Hopefully those breakout rooms were productive. It sounded like I flipped through them and, you know, people were getting the right answers. Let's go over the solution together just to make sure that everybody got that last one in particular. You know, it's the trickiest to calculate, but it's also the most accurate. So it's kind of the standard that we compare everything else to. All right. So here we go. All right, so the Hazen-Williams equation, boy, that looks terrible, doesn't it? Oh, should never use graph paper if you're going to scan it. That looks terrible. All right, so the Hazen-Williams equation is simple because the friction factor is constant regardless of the flow conditions, but it's not always the most accurate. What we should get is 3.85 meters for the head loss due to pipe friction if we use the Hazen-Williams equation. Now, what the Manning equation says about these same flow conditions is 6.73 meters of head loss. And so it's kind of overestimating what the head loss might be. And then the most accurate version is going to be the Darcy-Weisbach. And again, the reason why it's the most accurate, it's not just because it's the most complicated, it's It's the most accurate because it takes the unique flow conditions into account. So for instance, whereas Manning and Hazen-Williams equation didn't really take into account what was the Reynolds number, the Darcy-Weisbach equation does. And so if we have water here, which is a typical kinematic viscosity of 1 times 10 to the minus 6th meters squared per second, then that means for this 150 millimeter diameter pipe, then our Reynolds number should be 1.5 times 10 to the 5th. And then we use that Reynolds number in the Jane equation to get our friction factor of 0.024. So you can see that up here in the numerator is just the 1.325. And by the way, you may, when you go through different references or books, you may see a version of the Jane equation that looks slightly different than this. It has, instead of 1.325, it has a different constant in the numerator. That's just simply because that has been solved with base 10 logarithm rather than base e logarithm. So this has natural log ln. There's an equivalent equation that'll give you the same result in the end, but it's just using log base 10 rather than log e. So I just thought I'd mention that. So we put the relative roughness term together, and remember that you need to have the same units for the equivalent sand roughness, K sub s, as you do for the pipe diameter. And so one of the common errors that I see from time to time is that someone would have 0.26 as the K sub s, but then they would say 0.15 for the diameter, and then they'd end up with mixed units. And so it should be a ratio where the units are consistent. And then over here on the right-hand side of the Jane equation is our 5.74, and down in the denominator there, the Reynolds number to the 0.9 power. So that's where we get our friction factor of 0.024. And then substituting that into Darcy-Weisbach, we get that the head loss due to pipe friction will be 4.08 meters. And so Hazen-Williams was pretty close. Hazen-Williams got 3.85. So on a percentage basis, let me just see if I can calculate what percent error did the Hazen-Williams equation give us. So it's 4.08 minus 3.85 divided by 3.85. No, divided by 4.08, since 4.08 is the accurate truth, times 100, 5.6% error. So that's not so bad. Manning's equation, on the other hand, I think you get a sense now why we don't use Manning's equation to estimate head loss due to pipe friction in a closed conduit. It's simply, it has been constructed for open channel flow and is less applicable for closed conduit. So any questions on this example? All right, next we're going to use that template file that I emailed to you, the spreadsheet from earlier today. And we're going to use it to address this example. We have a pump that is lifting water, and it's also providing enough energy to overcome pipe friction. So if we're trying to get water from the lower reservoir into the upper reservoir, there are two things that's resisting the movement of the water from the lower reservoir to the upper reservoir. And one is the elevation difference. And so the pump is going to have to provide enough energy to overcome that delta Z. And then the pump is also going to have to provide enough energy to overcome the pipe friction that's associated with the flow rate we desire. So this problem statement says that what we hope to achieve is 1.5 cubic feet per second as the flow. And so the amount of head that is used for pipe friction varies depending on the flow rate. The delta Z is the same. So delta Z is going to be 35 feet regardless of whether we're using 1.5 cubic feet per second or 1 cubic feet per second. The amount of energy that the pump is spending to lift the water stays the same. But as you increase the flow rate, you're going to need progressively more and more energy to achieve those higher flow rates. And it's a nonlinear relationship too. Alright, so the first thing I wanted to do before we open up that spreadsheet and go through it together is just show you some hand calculations that have to do with how we calculate the pump head. Because we know it's 10 horsepower, and so I abbreviate that in the calculations just capital H, capital P. 10 horsepower, and by the way, the definition of a horsepower, if you don't remember, is that there's 550 foot-pounds per second in a horsepower. So this pump can achieve 10 horsepower. We're delivering water 800 feet away, so that's the length of the pipe that we'll put into the Darcy-Weisbach equation. We know the equivalent sand roughness for the pipe, so I've been calling that K sub S in some slides, epsilon in others. It's the same thing. What's just a little bit strange about this is that now we have traditional units here rather than SI units. And so a cast iron pipe has an equivalent sand roughness of 0.00085 feet. So what pipe diameter is needed? So we're going to use all of these equations along the way. We're going to use the kinematic viscosity of water, 1.22 times 10 to the minus 5th feet squared per second. Here's the relationship between the horsepower of a pump and the pump head, flow rate, and unit weight. So we saw the power equation back in fluid mechanics, but I only showed you the power equation in SI terms. So there it was P equals gamma Q HP. Here we're looking at it in traditional terms, so we've divided by the 550. So we'll use the Jane equation to determine the friction factor, and why this is an iterative process is we don't know how big the pipe needs to be to accommodate this. I mean, we could achieve 1.5 cubic feet per second through any diameter of pipe, depending on how much energy is available. But what we're saying is we're going to pair this 10 horsepower pump with a certain diameter of pipe, and we want those two combined things together to achieve the flow rate of 1.5 cubic feet per second. So I think you'll see how the pieces fit together as we go through it. But let's first look at these hand calculations that I was talking about earlier. Alright, so our unit weight of water is 62.37 pounds of force for every cubic foot of water. And so the pump head, H sub P, the head that the pump is adding, if we multiply the 10 horsepower by 550, because we want to, in the numerator, have the foot-pounds per second, and then in the denominator is our unit weight of water, 62.37 pounds of force per cubic foot of water, and then the flow rate of 1.5 cubic feet per second. You'll see that this pump is adding 58.79 feet of head. So if we go back to the sketch, the pump is adding 58.79. Some of that is going to be used for the delta Z. The rest of it is going to overcome the friction. So here in the energy equation, H sub P is 58.79. Location 1 is the reservoir. So the pressure at 1 is 0. The elevation at 1, we could say let Z1 be equal to 0. The velocity at 1 is 0. And then location 2 is this elevated reservoir where it's water in contact with the atmosphere as indicated by that little triangle. That means it's a free surface of water touching atmospheric pressure air. So P2 is 0, V2 is 0 because it's quiescent water that's not moving in a tank, and Z2 is 35 feet. So we've got 58.79 for H sub P, and then Z2 is 35, and then that tells us how much energy is available to go towards the friction loss. It's kind of, you can think of it as our budget, or this is an accounting process, and if we're adding a certain amount of energy and some of that is used for the delta Z, how much is left over to spend, so to speak, on the friction loss. Okay, so we're using 35 feet of head for the delta Z, which means we've got 23.79 feet to overcome pipe friction. Any questions so far before we move to the spreadsheet part of it? All right. So open up that template file that I shared with you earlier today, and hopefully you're rocking the dual monitors, whether it is like your TV is plugged into the laptop, or maybe you're watching this video on your phone or iPad and then you have your computer available, because having two screens is pretty useful when you're working through an example and you want to watch what I'm doing but then also have some other screen space to do your thing. I suppose you can always just split screens, right? But it's nice to have two screens. Alright, so here's the template file. We've got all the formulas that we're going to use, and let's fill in the known data to begin. Our pump is 10 horsepower. The equivalent sand roughness of this cast iron pipe in the problem statement, it tells us it's 0.00085. Okay? And then the unit weight of water, gamma, 62.37 pounds of force per cubic foot. Our kinematic viscosity, the water here in traditional terms, 1.22 times 10 to the minus fifth feet squared per second. So I will just type in here 1.22 E minus 5. And then that translates it to the scientific notation. The flow rate, 1.5 cubic feet per second. The pump we calculated before is adding 58.79 feet of head, and then the pump head, the friction loss, the portion of that energy that's available for friction loss is just the pump head minus the delta Z that we saw, which was 35, wasn't it? 35 feet? So that there's 23.79 feet that's going to be used on the friction loss. G is 32.2 in traditional terms, and our pipe length is 800 feet. All right, so now here's the conundrum. We don't know how big the pipe diameter needs to be, and D is one of the terms that goes into the friction factor F. So we're in one of those chicken and the egg scenarios where we don't know what F value to use yet because we don't know D, but we can't calculate D until we have an F value. So do you remember what's been our numerical strategy? Like, how do we proceed when we face this conundrum of we don't know the F value? What have we done before? Guess. Good, Benjamin. That's exactly right. Dalton says goal seek. We might be able to goal seek eventually, but at the first we have to guess, just out of thin air. So let's pick just some F value, 0.01. It's probably a little low. If we'd picked a middle F value, maybe it would converge faster, but this will be a good starting point just to prove that even with a bad F guess, it's still going to converge eventually. Okay, so now that we have this F value, we're going to calculate the diameter of the pipe that's required using this formula. Okay, so equals parentheses 8 times F. Now I'm just clicking on the cell where F is, but I'm not anchoring it because I'm going to want to copy and paste for subsequent iterations, and I want it to be a relative roughness. So I won't anchor the F reference, but I will anchor the reference to the length of the pipe. So I'm pressing the F4 button to give me those dollar signs. And then the flow rate, also, I want it to be an absolute reference, and so I am anchoring that. And we take it to the 2 power, and then divided by H sub F times g times pi squared. So pi open close parentheses to the power of 2. Okay, so you can see the formula up at the top. It kind of packed it in. I wish it was just going wide there, but oh, I've got an error. I forgot to close my last closed parentheses. And so it's suggesting that I should add one more closed parentheses at the end. So yes, that's fine. Okay, so if that's my f value, I think I've typed in a mistake somewhere. So that should not be the value I get. Let's double check. 8 times f times length times u squared. Oh, the 5th power. Good catch, everyone. Thank you. To the power of 0.2. That's more like it. I'm so glad that I have a bunch of smart students keeping me honest. All right. So just to reiterate what that formula is supposed to look like, it should be to the 1/5 power, which means to the 0.2 power. All right. All right, now so the area, that's easy enough, right? Pi d squared divided by 4. So pi times d squared divided by 4. Okay, so if my pipe has a diameter of 0.45 feet, then the cross-sectional area is 0.161 feet squared. And then the flow velocity, Q equals VA, so V equals Q, anchor reference, divided by A. So cell B17. Oh yeah. Didn't need that close parentheses. So 9.31 feet per second. And now I need to calculate the Reynolds number because I'm going to use that Reynolds number when I calculate the F value in my next iteration. So the Reynolds number, remember the formula is velocity times diameter divided by kinematic viscosity. So V times D divided by kinematic viscosity. Anchor the reference up there because I want it to always be looking in that cell for the kinematic viscosity. Okay. Now, the way that we would know if we're done is to calculate an updated F value with the Jane equation. And if the updated F value is the same as what you started with at the beginning of the iteration, then you know that's it. Your solution has converged, as they say. And so let's test and see. All I did just now is I highlighted this area. Oh, let's redo that. Redo. Okay. So highlight this and copy. So Control C. I'm going to put one space in between and Control V. And now I'm going to change a few things around. So this F value is, I shouldn't just use a guess now because I could do better than just a guess out of thin air. Now I could use the Jane equation, which will give me a more accurate estimation of F. And so now I'm going to type that in. So 1.325 divided by the logarithm of K sub S, here's that, anchor reference, and just take a quick note, that's in feet, so our diameter can be in feet, and that's fine. K sub S divided by 3.7 times D, so 3.7 times, and now the D that we're talking about is the previous D that we got from iteration 1. Okay, so that diameter, close parentheses, plus 5.74 divided by the Reynolds number. So which Reynolds number? The previous one, from the previous iteration, to the power of 0.9. and then I need to close that all the way and square it. So this is going to be my updated F value. And as soon as that calculation updates, all of the things below it are also going to change. Okay, so now this 0.0237, that's kind of like a middle value for F. Most of the time, F value is going to be pretty close to 0.02. So that makes me feel good, like we're probably on the right track. But we haven't yet converged because the F value changed and so did the diameter. So we need to do this again. But this was, by the way, this was iteration 2. It wasn't iteration 1. So I can just label it iteration 2. The great thing is, though, that now I can copy and paste. I'm not going to have to change any calculations. I can just Control C, Control V, and all I have to do is say, that's iteration 3. And it automatically calculates everything else. So we're getting closer. We went from 0.1 to 0.237. Now it's 0.0229. So it still changed a little bit. And so did the diameter. The diameter changed a little, not a lot. So let me do a fourth iteration. These subsequent iterations are so easy, I don't mind doing them. So here's iteration 4. The F value is stabilized, 0.0229. The diameter is more or less stabilized, 0.034. So like in practical terms, you're not going to find a commercially available pipe that's exactly that diameter. You know, if we're working in feet, there's going to be a 6-inch pipe, which would be half a foot, and then there's going to be an 8-inch pipe. So 8 divided by 12, so that's 0.67 feet. So what we would say here is we need a 8-inch diameter pipe, and so the solution is converged here. So I'm going to put a little note. Note, solution has converged. The exact diameter needed is 0.535 feet. So buy a 8-inch diameter pipe. Now the 8-inch diameter pipe, because it's bigger than it absolutely needs to be, what that means is that to achieve exactly 1.5 cubic feet per second, you'd need to put a valve after the pump and close that valve down a little bit. You'd need to introduce a little bit of local losses through a partly closed valve. So with that 8-inch diameter pipe, this pump is going to be a little more powerful than you need. So, you know, if it's okay to pump more than 1.5 cubic feet per second, then you don't need that valve. Like if this was a minimum and you just had to achieve that minimum, then you're golden. But if that's like the exact flow rate that's required at all times, then you need to have a pump, a valve downstream of that pump that you can close down because the pump's a little too powerful. But any questions related to the spreadsheet? We've got 1 minute remaining. If there was an uncertainty about how or why I did a certain thing, I'd be glad to address that before we go our separate ways for today. Hearing none, I'll remind you that homework 2 is due on Wednesday. So feel free to give me a call on Teams or on the phone or send me an email. The one thing that sometimes isn't a good way of getting a hold of me is the text chat within Teams. I don't get those alerts on my phone in the same way that I can see an email. So don't do the text chat on the, yes, there's a PC emulator as well. I highly recommend that you check out the HP. And you know, if you don't like it and it's not worth it to you, great, but maybe it'll be a good tool. All right, that's it for today, everybody. Hope you have a good one. I'll see you on Wednesday. Well, Harrison, if you don't mind spending the $110, I'm